Hi, in this video I'm going to go through radical substitution and some of the key points behind it. Specifically, I'm going to look at the mechanism. So first of all, we're going to look at what a radical is. So a radical is an atom or a group of atoms with an unpaired electron. So common one we're going to look at is chlorine. You may have seen a lone pair drawn before. So oxygen, when it's bonded, has two lone pairs, so we draw the pairs of electrons in. In a radical, we draw a single dot to represent a unpaired electron. The other group we're going to see today with them is the CH3 group with an unpaired electron as well. And the unpaired electron's around the carbon, which is why it's next to the carbon. On the left-hand side here, chlorine, I could have put it on the left-hand side or the right-hand side, it won't have mattered. So, there are 3 steps in radical substitution. And the purpose is to take an alkane, if you want to do this, and it's going to form a haloalkane. So alkanes, very unreactive, don't generally go many reactions. This is one way we can do it, which is take an alkane, turn it into a haloalkane. So first step is initiation, and in initiation our chlorine, so Cl2, is going to go into 2 radicals, and it does this because of UV light. So UV light is going to shine down. We'll have our chlorine bonded to another chlorine, and now they've each got an electron there. Let's get a different colour pen. And what's going to happen is this electron is going to go back into that chlorine, and this electron is going to go back into this chlorine. Notice I'm just using half arrows. This represents that just one electron's moving. Now this is homolytic fission. So homolytic fission is where one electron goes back to one chlorine, one electron goes back to the other to form radicals. Heterolytic fission is if I take CH3 and Cl, where both electrons go into one species, and that's represented by a full arrow. So this would lead to CH3 plus and Cl minus. Electrons gained, chlorine's gained the electrons. The methyl group has lost the electrons. In a free radical, in homolytic, we'll get a chlorine free radical and another chlorine radical. There. So that's our initiation step anyway. Chlorine, in the presence of UV light, is going to break down into 2 of these chlorine radicals. So once we've got that, this is a very reactive species, and after the initiation step, we're then going to get the propagation step. So we've got our free radical now, and that is going to react with our alkane. I'm just going to use ethane, but it could be any alkane. Yeah. So have our ethane, and that is going to form, first of all, the Cl dot, which is very reactive, is going to take one of the hydrogens, and that's going to be HCl. now. Notice the radical has disappeared. It's just HCl. That radical has been swapped and is now on one of the carbons that was that ethane. This is the first step in our propagation. That free radical now, though, is floating around, and if that combines and effectively combines with another chlorine molecule, so remember right at the start we had chlorine that was separated by UV light. Some chlorine won't have been separated by UV light and just be floating around. That chlorine can then combine with this radical to go back to then, first of all, a chlorine radical plus our haloalkane, C2H5Cl. So we've got here haloalkane forming, some hydrochloric acid forming, and our chlorine radical, which can go all the way back again and go through the first propagation step. So the propagation steps just keep on going round and round and round and round. It only ever stops if we get to a termination step. And these are quite rare, but when they do occur, then that ends the reaction that we've got. So a termination step is if then we have two radicals colliding. So it could be we have our two original radicals collide, and if they effectively collide in the right way, they will go back to being chlorine. Or we had C2H5, but a C2H5 radical formed at one point. They could collide instead, and they'll form butane. Or a mixture can collide, where we get C2H5 and this chlorine radical colliding to once again form our haloalkane that we want. So that's our initiation, propagation, and termination. Our overall equation for this would be Cl2 plus C2H6 goes to, and these are then the products from the propagation step. We'd have hydrochloric acid, or HCl, and C2H5Cl. There are some products from the termination step though as well that we could technically put in there and get longer chains, but these are very rare that we get the termination kind of steps occurring, and only in very, very small quantities. So if you wanted a reaction to produce C4H10, this is not the advised reaction to do, because you'd be in such small quantities. So the problem we get from this is, though, yes, this is a way to produce haloalkanes from alkanes. It's producing, in lots of different examples, more than one organic compound. So then that becomes a bit of an issue in kind of isolating and going after them. We can get further substitution as well. So in the propagation step, we had C2H6 going to C2H5Br. But then that can further substitute, and we get C2H4Br2, which can further substitute CH2H3Br3, and so on. So we can get further substitution. We also, if we had a longer chain, so we can get substitution at different positions in a carbon chain, we can't direct where this radical is going to go. So if we had butane, C4H10, reacting with chlorine or bromine, whatever halogen we're reacting it with, we could get it substituting onto the, so Br2 in UV light, it could substitute onto the first one, or it might substitute onto the second carbon. Never too sure where it will go and how we direct that. Plus, we could get more produced there. So it's not a particularly effective reaction for producing compounds that we would like. And that is free radical substitution.